Still working on electrolytic cells here, and something unusual is going to happen with this one. So they give us a solution of potassium sulfate, which would mean we'd have potassium ions, and we'd have sulfate ions. And they tell us it's aqueous, so we have H2O. Did you notice in the previous practice they kept saying that everything was molten? That's a way that you can liquefy an ionic compound and get it to break up into ions so that things can react. The other way to do that is to dissolve the thing in water, because that also gives you ions and you have a liquid for everything to move around in. So why would we bother with the molten thing when an aqueous solution works just as well? Well, let's take a look at the redox table and see what happens here. Potassium sulfate. So this is our list of ions, K+, sulfate, and water. And if we hook up a power supply to that, what are we going to get? Our strongest oxidizer. We don't have fluorine, we don't have this. No. We're looking for K, SO4, or water. This is interesting, but we don't have an acid solution, so we can't assume we have hydrogen ions, so that's no good. The search continues. Sulfate, but only with lead, so don't have that. Potassium sulfate or water, potassium sulfate or water. Here is water. Water is our strongest oxidizer. And so we're going to get 2 H2O plus 2 electrons makes hydrogen and hydroxides. Take that back over to the question, sorry. 2 H2O plus 2 electrons gives us okay, gotta get that right. Yeah, okay. So that's one of our reactions, and the other one, for the strongest reducing agent, sadly we don't have K, metal, so we can't count on that. We're looking for K plus or sulfate or water. K plus, sulfate or water. Here's sulfate, but only with lead metal, that's no good. K plus, sulfate, water. Sulfate, that's hydrogen peroxide, don't get fooled by that. K plus, sulfate, water, turning into oxygen and 4 hydrogens and 4 electrons. Okay, so turns into oxygen, 4 hydrogen ions, and 4 electrons. So, when you see something like this, it's very natural to kind of discount the water and say, okay, clearly the interesting chemicals, potassium and sulfate, are going to be the ones that do stuff in this cell, and you expect to see potassium and sulfur reactions. Not always true. Sometimes the water is actually the most active species in the cell, and it's the one that does everything. In this cell, you put potassium and sulfate in here and you stand there waiting for potassium and sulfur reactions to start happening, and instead they just sit there doing nothing while you electrolyze the water. So that's why we sometimes use molten cells, because water can get in the way. It can react and keep what you intended to be the stars of the show from doing anything. So in this cell, to finally answer the question, what would happen in here? Well, I want to combine these two reactions, but right now I have 2 electrons versus 4. That's no good. So double the first reaction, 4 H2O. Double that, that's 4 electrons. Double that, double that. And now we can add these two reactions together. Cancel the electrons. And I'm going to simplify this a little bit on the way. 4H2O plus 2H2O makes a total of 6H2O. And on the right, we're going to get 2 hydrogen and an oxygen. And you see what's going to happen here? This is like pure acid versus pure base. We have 4 hydrogen ions, 4 hydroxide ions. These will certainly react. It'll be like an acid-base neutralization. And they will combine and make water. We'll get 4H2O off of that. If you're completely unfamiliar with acids and bases, you could just think of this as positive ion plus negative ion. These will certainly combine, and the product is very stable, so it'll stay together. And we can simplify this reaction a bit because there are spectators in it. We have 6 water on the left, 4 water on the right. We can cancel 4 water from each side. Get rid of all of those. Get rid of 4 of these, so only 2 remain. And so our overall reaction says that 2 water molecules will be electrolyzed, broken down, and that'll produce hydrogen molecules and oxygen molecules. Quick pause. Skip ahead if you're not interested in side notes, but this is too cool to not bring up. For a very long time, chemists thought that water was an element, that there was nothing inside water. It was just one of the building blocks of the world. And it was a very big deal when a chemist put an electric current through water and actually tore it apart. That was shocking. They found out that water was not a basic building block. It was made of 2 other things. And not only that, they found that these things were oxygen and hydrogen. And the fact that it was 2 to 1 was an important discovery when they were figuring out how formulas worked. It was always, no matter how much water you broke down, you always got exactly twice as much hydrogen as you did oxygen. And that led them to the idea of atoms, where water is made of 2 hydrogen pieces connected to 1 oxygen piece, and that's where the formula H2O comes from. You can do this with balloons and watch the hydrogen balloon inflate twice as fast as the oxygen balloon. And that's some of the really strong evidence for there being 2 hydrogens to 1 oxygen in a water molecule. So a lot of really important science is packed into this little reaction, even though it's not the reaction you might have wanted when you set this up. Okay. Getting back to work. Sorry, I thought that was too neat to not mention. Lead nitrate aqueous again. So in this cell we have lead 2 ions, we have nitrate ions, and of course we have H2O. Will they do the water thing twice? Let's find out. Lead, nitrate, and water are our possible characters. So back to the redox table, and off we go. Lead oxide, nope. We want lead, nitrate, or water. Lead, nitrate, or water. Lead, nitrate, or what? Here's nitrate, but it would have to be acidic for this to work, so that's no good. Search continues. Lead, nitrate, or water. Lead, nitrate, or water. Here's lead ions. Lead will be our strongest oxidizing agent. Lead 2 will pick up 2 electrons and turn into lead metal. Let's get that into the problem right now so we can feel like we're making progress. So one of our half reactions is lead 2 plus 2 electrons, lead metal, and now we go back looking for our SRA. Start at the bottom. Lead, nitrate, or water. Lead, nitrate, or water. Lead, nitrate, or water. And it's lead ions I'm talking about. So when we see like lead metal here, that's no good. Lead metal again, still no good. We want lead, nitrate, or water. Nope, water. The water reaction is going to happen again, so H2O turns into an oxygen, 4 and 4. Okay, so in this case, at least the lead got to react, but we do still get the thing where water gets involved. And if you were hoping for the nitrates to react in some way, it's not happening. So, those are our two predicted half reactions. We want to combine them, but we can't because electrons don't match. Double the lead reaction to make them match. 2 lead, 2 times 2 is 4 electrons, and 2 lead. So now we have 4 electrons versus 4 electrons. That is good. Now we can cancel the electrons and write our net reaction, which will be 2 lead 2s plus 2 H2Os, 2 lead metal plus oxygen plus 4 hydrogen ions. Okay, and I remembered while doing this one that they also asked for the potential difference, which I forgot to do for part A. I'll have to circle back, but let's take care of this one first. Lead 2 reducing to lead is right here, and its reduction potential is minus 0.13 volts. So for this reaction we have negative 0.13 volts. The other reaction is the oxygen-hydrogen 4 electrons to water thing, and that, there we are. In the book, it's 1.23 volts, but we were starting on the right side. We have this reaction going in reverse, so we're going to get minus 1.23 volts from it. Minus 1.23 volts. When we add these two half reactions together, we add the voltages together, and we get minus 1.36 volts. Negative, meaning this reaction won't happen by itself, and if you want to force this reaction, you would need a power supply that's at least 1.36 volts, preferably more. Technically, 1.36 would not be enough. You need more than 1.36 volts because the net voltage needs to be positive for a reaction to occur. So, that takes care of the voltage there, and let's circle back and do this one while we're at it. This is the two water reactions. So, we had this reaction going in reverse, that's minus 1.23 volts, and we had this one going forward, which is minus 0.83. So, sorry I got this out of order, but this reaction is minus 0.83 volts. This one would be 1.23, except we're doing it backwards, so for us, minus 1.23 volts. Add those together and we get minus 2.06 volts. That's what it takes to electrolyze water. Okay. New thing, aqueous solutions of, okay, so aqueous, we have water. Sodium bromide, we have sodium ions. We have bromide ions. We have zinc ions. We have chlorine ions. Mixed together. Graphite is highly unreactive, and we know it's not on our redox table, so I'm not going to bother including that. It's never going to be our SOA or our SRA. But we do have all these things, and this is quite a list, so I thought I'd drag that with me. But water, sodium bromide, zinc chloride. I'm going to have to try to hold that all in my head, which is not going to be easy. In fact, it's probably not happening. I'm just going to copy those again. Water, sodium, bromide, zinc, chloride. Okay, those are our candidates. And now we go through the redox table looking for any of those things. Sodium, bromide, zinc, chloride. We have chlorine, but that's not what's in our cells, so no luck there. I'm afraid water is going to be our SOA, which would be a bit dull, but let's see. Sodium, bromide, zinc, chloride. Sodium, bromide, zinc, chloride, or water. There's bromide, but only with silver, so that's no good. zinc. Okay, we were about to hit water, and that could have been our strongest oxidizer, but zinc saves the day. Our strongest oxidizer is actually the zinc ions. So, back here in the problem, our SOA is zinc. It'll take 2 electrons and become zinc metal. And while I'm at it, let's do this a little smarter. As soon as I find this, I can get the cell voltage, or the half reaction voltage. It's minus 0.76 volts. Minus 0.76 volts. Okay. Half done. Now we're reading up the right side looking for sodium, bromide, zinc, chloride, or water. Nope, 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 sodium, nope. This is sodium metal. We have sodium ions, so that doesn't help us. Sodium, bromide, zinc, chloride. We don't have zinc metal, so this doesn't help either. Sodium, bromide, zinc, chloride, or water. Sodium, bromide, zinc, chloride. Here's chloride, but it's with OH. We don't necessarily have that. Bromide ions right here. We were pretty close to hitting water, but the bromide ions are actually going to step up. So we're going to get bromide ions turning into bromine. And the voltage for that, here it's listed as 107, but we're doing this reaction in reverse, right? We're starting on the right side and going this way. So we're going to get minus 1.07 volts. Minus 1.07 volts, and that's for bromide ions turning into bromine and releasing 2 electrons. So we want to combine these, and we can. We finally got one where the electrons just match, so we don't have to do any extra work there. We can just combine these 2 reactions, and we get zinc ion reacts with 2 bromide ions to produce zinc metal and a molecule of elemental bromine, and add those together and we get minus 1.83 volts. Not too bad, I hope. One more. Aqueous solution of sodium sulfate. So we have the aqueous thing, we have sodium ions and sulfate ions. Aqueous sodium sulfate. Okay. Go to our list. That gray is old stuff. Let's get that out of the way. Okay, so we have water, sodium, and sulfate. Try to do this one a little faster. Water, sodium. This is sulfate, but irrelevant as requires other stuff. Water, sodium, sulfate. Water, sodium, sulfate. If you had water with oxygen dissolved in it, that would be. Then this could be our reaction, but we do not. If we had acid, then this reaction would work. This is for sulfuric acid, but we don't. So water, sodium, sulfate, water, sodium, sulfate, water, sodium, sulfate. Water is going to be our SOA. So this thing again, the one with hydrogen and 2 hydroxides, and its voltage is minus 0.83 volts. Can I hold all that in my head? Was it 87? I failed to hold it in my head. 83. And it's hydrogen, not hydroxide. Okay. You're watching my brain turn to mush right before your eyes. Sorry about that. This produces hydrogen, 2 electrons, and minus 0.83 volts. I didn't flip this because this reaction is as written in the data book. Good so far? Now we go to the right side and we look for our strongest reducing agent. We have sodium ions in our cell, but we don't have sodium metal, so this doesn't help us. Water, sodium, or sulfate. Water, sodium, or sulfate. Water, sodium, sulfate. Da, 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 da. It's this again. We hit water. This is another reaction like the first one where the sodium and the sulfate don't do anything, and when you turn on your power supply, you just electrolyze water. The other things you added in there, the sodium and the sulfate that were supposed to maybe be your reactants, don't participate. The water gobbles up all the electrons, and so we get 2 waters turning into 144. And we're writing that one in reverse, so we flip the voltage to minus 1.23. So anytime you take water, if you put really weak oxidizers and reducers into it, they're not going to do anything, and when you try to electrolyze those other chemicals, you're just going to electrolyze water instead. And so every time this happens, you're going to get the same reaction as in A with its minus 2.06 volts. And I'll add this together one more time, but you've already seen it. Double the first reaction to make the electrons match. So 4, 4, 2, and 4. And now we can cancel the electrons. 4H2O plus 2H2O makes 6H2O for the moment. We get 2 hydrogens. We get an oxygen. And these combine to make 4H2O. And then we can erase 4 water from the right side, all of it, and 4 water from the left side, leaving 2. This is our net reaction. Water will break down into hydrogen gas and oxygen gas, and the sodium and sulfate won't